Hello, Calc AB. This first side is pre-calc with a little bit of a calculus twist. So we're going to be evaluating the following end behavior limits and then writing the equation of the horizontal asymptote. Anytime a direction asks you about end behavior, they're asking about the limits at the infinities. So we don't really care so much about what's happening in the middle of the function. We just care about what's happening at infinity and at minus infinity. If you remember from pre-calc, when you go to infinity and you're dealing with this cubic over a cubic, infinity is so large that I'm going to cross out the things that no longer matter. I know that they're kind of big when you go to infinity, but the 5x cubed is way bigger, and the 7x cubed is also way bigger. So this other stuff just is like pennies relative to like thousands of dollars. So we let that go away, and so the limit goes to 5/7. A similar argument is made for b. I'm going to cross out the stuff that won't matter. And even if you're plugging in a negative infinity here, you really should pay attention to the fact that it's a cubic, and so that number will be negative. But your denominator is also behaving the same way, and so it is also going to 5/7. The equation for the horizontal asymptote is y equals 5/7. Make sure you've got an equation there. Number 2. Different functions, but it's the same kind of idea. So I'm going to cross out the things that won't matter anymore, and x to the 7 over x cubed becomes x to the power of 4. When you go to infinity, this will also go to infinity, but notice the negative coefficient. So we have this going to minus infinity. Same thing happening in part B. A negative to a power of 4 is positive, and so you have the minus infinity for this limit. Therefore, there is no horizontal asymptote because there is no limiting value. We would say that the function diverges and it just keeps going down to negative infinity forever. Number 3. This one looks scarier than it is. You're going to cross out the things again that won't matter when you go to infinity. And that's really only paying attention to the two fractions first. So looking at the first fraction, the plus 5 will not matter, but you're always adding 6 to this fraction. So that's the part that matters. In this second fraction, the plus 4 won't matter. So I'm going to rewrite this. This is really like 6 plus 1 times 3. And so that becomes 21. Same argument is made for b. So this is also 21. Therefore, the horizontal asymptote is 21. Number 4. The limit as x goes to infinity of tangent of 1 over x squared. When you try to substitute in something very, very, very large, that makes your denominator get even larger because you're squaring this term. 1 divided by something large is going to be 0, and the tangent of 0 is 0. Number 5. The limit as x goes to infinity of x minus 1 over the absolute value of x minus 3. This is a pretty interesting example, and it's one that you should remember. The minus 1 and the minus 3 will not matter, but the absolute values, like this does not just cancel out to be x. You need to pay attention to what's being substituted in. You know that absolute value will always be positive, and because you have an infinity, which is positive, this is something positive divided by itself, which is positive, so this limit goes to 1. But in b, when you substitute in negative infinity, your numerator will be negative and your denominator will be positive because of the absolute value. So that means you have a limit that goes to negative 1. This has two different asymptotes, and you have two different end behaviors because you have one at infinity and one at minus infinity. So we have y equals 1 and y equals negative 1. So in summary, end behavior discusses the horizontal asymptotes, if any, and in calculus, that is the limit as x goes to infinity and as x goes to minus infinity. You can use your calculator just as we did the other day to evaluate these limits. Notice the limits are they're taking x to infinity. And when you do this on your calculator, you get 0 here. When you take this function to minus infinity, you also get 0. And I want you to know the reason why. This is something that you can explain back to me that I think it's important that you be able to explain back to me. And it's because the sine function looks like this. The sine function goes on and on forever, and it's what we call a bounded function. So it will never go above 1, and it will never go below -1. When you start to divide by something that gets huge, it won't matter what your numerator is, because between -1 and 1, those numbers are pretty small, and you divide by something really, really, really big, that's going to make it go to 0. We use those facts to help us with the limits in 7 and 8, just as we did yesterday. So the limit as x goes to infinity, I see this fraction, I'm going to break it down into 2 different fractions. Here we have x over x go to 1, and the sine x over x going to 0. So 3 plus 0 is equal to 3. Number 8, break it into 2 different ideas. This first limit goes to 0, and then you can subtract 5 because the function is always 5 regardless of where you are, so that limit is -5. Number 9, same idea except with cosine. Those limits are both 0 by the exact same reasoning, and again I think that's an important idea. Cosine looks like this, and it's a bounded function. It will never ever be greater than 1, and it will never ever be lower than -1. So you take those relatively small numbers and divide by bigger and bigger numbers, and it's going to go to 0. Evaluate the limit in number 10, breaking it down into 3 different limits now. The first limit goes to -2, the second limit goes to 0, and the third limit goes to 0. Your final answer is -2. Number 11 breaks down into 2 limits. This first limit will become 0. When you simplify x squared over x, it becomes x. When you substitute the minus infinity in, this is 5 times minus infinity, which is still -infinity. The double negative here will make the overall limit infinity. Go ahead and try the challenge, and let me see what you get. Go ahead and start working on your homework after that, and I'll see you guys tomorrow.